Welcome back. In our last video, we were able to look at the definition of the Moivre's theorem, as well as what happens when you take the product of two complex numbers in their polar form, as well as what happens when you take the division of two complex numbers in their polar form. This time around, we want to now consider what the root of a complex number would be, how exactly it can be defined, and how to use this. As always, make sure to like and share and subscribe. Now, let's start. First and foremost, we will define a complex number in its polar form. So where R is, of course, the modulus, and then theta is the argument of the complex number. Then we say that the nth root of the complex number, or the nth root of z, is in fact, let's call it w, which will be z raised to the power of 1 over n, which of course would be the formula for the root of this complex number in n terms. Now, we first and foremost can write this formula in a short form. So we can write it as CIS theta plus 2k pi over n, right? Where k, of course, is just a counter, 0, 1, 2, till you get to n minus 1. Now, of course, if you are seeing this CIS notation for the first time, it just means the cosine plus I sine, right? So we can write it in full as W is equal to R raised to the power of 1 over n into cos theta plus 2k pi over n plus I sine theta plus 2k pi over n, right? So this and this mean the same thing. Now, basically, the number of roots you have is dependent on the value of n. So if you have like a square root of z, that means you're going to have two values for that root. If you have the cube root of z, you're going to have three values for that root. If you have fifth root of z, you're going to have five possible values for that root, and so on and so forth. So this is exactly how the formula representation looks like for the root of a complex number. Let's take an example and see exactly how we can generate or write the roots of a complex number. So in this case, we are to find the seventh root of the complex number 1 plus I. Now, this is what we have. The first thing, of course, we need to convert this into its polar form. We need to find its modulus, and we need to find its argument. Remember, if you compare with z, which is equal to x plus iy, we will have that r, which is the modulus, is going to be the square root of x squared plus y squared, and then we'll have that theta will be equal to the arctan of y over x. So now, based on this, of course, from comparison, we would have that x will be equal to 1, and then we'll have that y is also equal to 1. Those are our two values that we have gotten. So if you use that together, it will mean that r would be equal to the square root of 1 squared plus 1 squared, which of course gives you the square root of 2, and then theta would simply be the arctan of 1, because y over x would be 1. And this, of course, would give us pi over 4. Remember, our values are meant to be in radians. Our values are meant to be in radians. So pi over 4 rads. You can write it together. Now, if this is the case, that means our z, of course, can be written as 1 plus I, and also as root 2 into cos theta, which is pi over 4, plus I sine pi over 4. This is the value of z. So if we are now looking for the seventh root of z, remember the formula tells you that you just take the polar form and then you have the roots coming at the stops and at these positions. So in that case, therefore, we would have that z is to the power of 1 over 7 would simply be root 2 is to the power of 1 over 7 multiplied by, so let's write our general form, cosine of pi over 4 plus 2k pi over 7 plus I sine pi over 4 plus 2k pi over 7. Where, of course, k will go from 0, 1, 2, till this time around, till 6. Hence, we will have 7 roots in total. So, if we put this all together and we seek to find our answer, we'll have that when k is equal to 0, would have our first root, let's call it W1, would be, of course, we could write this in a full initial form. Root 2 is the same thing as 2 raised to the power 1 over 2. So by law of indices, that's the same thing as writing 2 raised to the power of 1 over 14, right? And then inside, when k is 0, that means 2 times 0 times pi vanishes. So we're going to be left with cosine of pi over 28 plus I sine pi over 28. This would, of course, be the very first root. The second root, when k is equal to 1, let's call that W2, that would simply be, again, 2 raised to the power 1 over 14, that remains constant, and then this time around k is equal to 1. So you have 2 times 1 times pi, that's 2 pi, then you add that to pi over 4, right, that gives you 9 pi over 4, then divided by 7. So you're going to have this to be cosine of 9 pi over 28 plus I sine 9 pi over 28. The same thing happens when k is equal to 2, right? Here we would have W3, which will be 2 raised to the power 1 over 14 when k is equal to 2. Put that into the substitution, we would have the cosine of 17 pi over 28 plus I sine 17 pi over 28. And the process continues when k is equal to 3. When k is equal to 3, we have W4, that's the fourth root. That will be 2 raised to the power of 1 over 14, right, of the cosine of 25 pi, right, because when k is 3, this will be 6 pi, that will be 24 plus 1, that's 25 pi over 28 plus I sine 25 pi over 28. Then when k is equal to 4, that will give us the fifth root. In this case, we have 2 raised to the power 1 over 14. Notice that the angle or the radius or the modulus is not going to change in all of this process. So in this case, you are still going to have the cosine of, this time around, 33 pi over 28 plus I sine 33 pi over 28. Now, we have, of course, done quite a couple of this, enough for you to have already start seeing a pattern within the angles. You'll see that these angles are always increasing by a value of 8 pi over 28, right? So here, if you add 8 pi over 28 to this, you get this. If you add 8 pi over 28 to this, you get the next one. If you add 8 pi over 28 to it again, you get the next one, and so on and so forth, till you end up at the last term. So what you would notice is you essentially are working towards that increment. Now, what exactly does that increment tally to? We'll be able to see something interesting when we finish all the roots. Remember that all the roots must be in the same region, which means they must always be within that same circle, which is between 0 to 360 degrees, right? At no point in time should they exceed 360 degrees. If they exceed 360 degrees, they will become a duplicate of one of these roots. We will see why in a minute. So we continue to the sixth root. This time around, we would have cosine of 41 pi over 28 plus I sine 41 pi over 28. And then the last root, which is our seventh root, we have W7, which of course will be equal to 2 raised to the power 1 over 14 cosine of 49 pi over 28 plus I sine 49 pi over 28. And this would be our last root. Now, if you pay attention, you would notice that at this point, you would have done just enough to retain or remain within the representation of 0 to 360 degrees. Don't forget that 49 pi over 28, when you break it down into angles, will give you a value of 315 degrees. So if it gives you 315 degrees, you see that it still falls within 360 degrees, which is just what you need to represent all the roots. You notice that the moment you go beyond and you try to find a next root, the value you are going to find will be a duplicate of the first root. You can try that out and see that this actually happens. So this is basically how to use the formula for the roots of a complex number. It's very straightforward. It's just about finding the modulus, finding the argument, and imputing it into the formula. Once you're able to do that and you're able to take notice of the value of k, then you're able to solve. Now that we have looked at this, in our next video, we will look at how exactly this works into the concept of the nth root of unity. So when you have a question that tells you to find the nth root of unity, how exactly can you deduce this? You can do this using the same formula of the roots of a complex number. So we'll definitely proceed to this in our next video. As always, like, share, and subscribe, and I'll see you there.